Okay, I've started recording on my end here, so we'll give it another minute here and then we can get started. Looks like we have 22 attendees right
Okay,
now.
Kirk, I think everybody is unmuted. So if anybody has any questions, you can just.
Okay, is there anybody here that didn't take the last lecture or had a chance to look at it? If so, you should be able to find that material either on Michael's website or the www.hdlexpress.com/HPSDR, and that's capital letters HPSDR. So today we're going to have lecture 2, and we're going to start off where we left off last time, and we're going to talk about registers today. And we're also going to talk about memories. That'll be the first items we talk about. Then we're going to talk about size of operations, because that's important in all that you do in your code, is learning about the size of operations. The third thing we're going to talk about are flow control statements. Those will be things like if statements, case statements, case Z and case X statements. Something new, a little different than software's case statements. Then the fourth item will be loop statements. So we'll go over forever loops, repeat, while, and for statements. Then we're going to talk about subprograms. There's two things called functions and tasks. So let me set my screen up here. So registers are variables that are used to store values. And for registers, they can either be scalar, which are 1 bit, or vectors, which are n bits, or integer, which are 32 bits, time, which are 64, or real. So let's take a look at the declaration syntax. Now, if you were in the last lecture, you recognize that this is kind of a placeholder for an identifier, and in this case, this is an identifier list. Okay, and identifier list can be separated by commas. So we're going to have an example in a minute, but you can refer to this or a Verilog book to see the basic syntax. You can optionally have an MSB, LSB index, so you could have a size, and here's syntax for integer, time, and real. So let's take a look at where registers are used, where they're declared in the module. Notice that they're declared in the module and that they're accessible by the always or an initial block. Okay, with multi-bit registers, you have an unsigned value with the MSB on the left. So here we go. So here we have an 8-bit register called byte, and it's 8 bits wide, and it goes from 7 to 0. Here we have one that's 16 bits wide, and it goes from 1 to 16. Got the opposite order. Here's one that goes from 63 to 32. It's a 32-bit word, and here's 1K, and this one goes from 1023 to 0. My guideline is don't use these formats here. Always go from n to 0. Be a lot better off. People will understand your code a lot better. So that's just my guideline, even though you can do things like this in Verilog. So let's take a look at a declaration here of word. We've declared it to be 16 bits wide. It goes from 15 to 0. And if you were to, and I'll show more examples of these, but you can access the entire vector. You just say word. So the width of this right here is 16 bits. You can also access single bits. So like if you want to access bit 4 or bit I or something where you've made a calculation for a particular bit. You can also access consecutive bits, and this is known as a part selection. So here we said word 70. Now it's 16 bits wide, so we're accessing the lower byte of it. Here we're accessing the upper 2 bits. Okay, and the indexes need to be constants. and they should follow the direction of the declaration. So the direction here is from 15 down to 0. So in this case right here, I plus 3 down to I, that's in the same direction. Okay, this would not be good. Wrong direction. Oh, yeah. Just a minute, I lost my window. Okay, in Verilog there's no bounds checking, okay, and there's no runtime or compile time errors. So you have to be very careful with your indexing, okay, and your results that you're going to get if you go out of bounds is going to be undefined. So in this case we have a 16-bit register called word. It goes from 15 to 0. So if you were to select 16 or 31 to 16 or whatever, there's no telling what you're going to get. Okay, so it's up to you to be very careful. So let's look at register assignment. The basic syntax is you have a target and you assign it some expression. Okay, let's say we want to assign that word equal to some expression, or just a bit of a vector to some expression, or a part selection to some expression. All of these are valid. Now for concatenation, that's what this line is right here. This with the curly brackets, this is known as a concatenation, where we've concatenated two or more items together. So the concatenation is right justified. So in this case, word is 16 bits, and we're going to select part of them to go here, 8 bits to go here, and 8 bits to go here. So this is valid to do. You can do a byte swap in this case. Or you might do something, let's say you had an instruction, you were going to do some instruction decoding, and this was 32 bits, and maybe CPU reg was 8 bits, and address was 16, and so on for the rest of the bits. Now if the size of instruction is bigger than the size of all of these, then it's going to be right justified. It's going to use the lower bits of this to fill in these values. So memories are just arrays of registers. You can use reg, integer, and time only, no real. And they're one dimension only. And I'll show you what we mean by that. Here's the syntax. You have the type, such as reg, integer, or time. And then you have a name, such as mem 1, 2, 3, or 4. And then you have a range. So here we have min 1 goes from 255 to 0. Here we have mem 2. Now it's 8 bits wide, and it goes from this value, 16 hex FFFF, down to 0. Okay, so you have that many of these 8-bit wide memories. And again, you can use indexes, but it's preferable if you go from 0 to some value or some value down to 0. Try not to start off as some non-zero value. Now memories are accessed one location at a time, and there's no runtime array bounds checking. So let's say that we have a 32-bit wide RAM, and we have 256 locations of that 32 bits, or different 32 bits. Okay. This is a valid statement, assignment. I can assign to RAM 0, which would be this one. So that's a full 32-bit wide. RAM 0 is 32 bits wide. I can assign it the 32-bit wide value of RAM 1, right shifted 4 bits in this case. That's okay to do. It's not okay to do more than one memory location at a time. Okay, you can't do a memory, what's called a memory slice here. I can't write to 0 and 1 at the same time here with this 64-bit value in this manner. Now I can do it in this manner. because this is the same as two writes, so to speak. If you're outside of the array, so it only went from 0 to 255, if you're outside, there's no telling what's going to happen. You cannot arbitrarily access bits inside a memory. You must use a read, modify, write operation, hence the name memory. Okay, so in this case, we have RAM. It's 8 bits wide. We have 256 locations for it. So we have, what the person is wanting to do here is access or change the lower 4 bits of RAM 0. So they tried to do RAM 0 and then the lower 4 bits of that. Can't do it. Okay? The way you have to do it is you'd make something, maybe a temp register. You'd assign RAM 0 to that temp register. Then you can modify the lower 4 bits of that temp register and then write temp right back out to RAM. Now we're going to look at size of operations. Okay, this is important, and some of the rules you may have to just refer back to until you get used to it. Oops, sorry. Okay, operands and results of operations have a specific size. Also, expressions are evaluated using the largest size. Remember these two rules real carefully now as we go on with the next examples. Operands and intermediate values are truncated or zero field is needed. No Z, X, or sign extension. Excuse me, I've got my chat window's in the way. I'm having a hard time figuring out where to put my chat window. It's over my text. Oh, remember that unsigned constants default to 32 bits. Okay, so here's some size of operations. Let's say we wanted to do an addition or subtraction or multiplication or any one of these operations right here where you're going to operate between two operands here, I and J. So you got I plus J. The size of this operation is going to be the max of size of I or size of J. So here we see these are the basic rules, and you should find this in any Verilog book. Okay, and you just kind of have to go and refer to it a while until you get used to this. So that's going to be the important thing to remember for size of operations, is to refer back to a table until you're used to it. So the other day, now remember that we did comparison operators and identical operators. Those type of things, the size of the operation was 1, if you remember. Okay, do you remember what these operators are? Where you have the operator and then some identifier. Do you remember what that is? Those are called reduction operators. So like an AND reduction, you have the ampersand in front of the identifier. So it ANDs all the bits of however wide that register or whatever is. So now let's take a look at some examples. Here I've declared count to be an 8-bit wide register. And in this statement, I said count equals 1 tick B1. Okay, so what's the size of this? It's 1. What's the size of count? It's 8. What does our rule say? Do I have it listed here? Where is it? Anyway, this is evaluated with the max. Oh, yes, the rule is right back here. I forgot it. Expressions are evaluated using the largest size. Okay, so the largest size in this example is 8. So this will just get zero filled out to 8 bits wide. And so, I'm sorry, that should be a 1 there. I made a typo because I edited this afternoon and added this in. Okay, so the result here should be a 1, and it'll be 8 bits wide. So in this case, what's the maximum size? It's 3 bits. So the result is going to be 3 bits. Okay. So when we multiply 2 times 4, The result would be 8, but the maximum size here is 3, and that's the result. So notice we lose a bit there. So again, you need to be careful about what size you use. Okay, same thing here. The maximum size of either one of these two is just 1. So we're going to lose that most significant bit because the result is going to be 1. So what we should have done here is if we want to add them, just declare these as 2-bit wide. So you're going to have to remember some of these things and remember these size of operation. Now this one's a little different, I believe. Let's take a look at it. Okay. Now the evaluation, remember, let's go back again here. Expressions are evaluated using the largest size. So let's go back to this. The largest size here is 2 bits. Largest size here is 1, but since we're using 2 bits, the evaluation is going to be based on 2 bits. So instead of this truncating, it's actually going to become the value of 2, and 2 is equal to 2, so the result, remember the result of the operation in this case is going to be just the 1 bit, because this is a true or false, right here, when you do equal, not equal, those type of things. Size of the operation is 1. So this might be a little different, and you just have to get used to this. Here we have a register, 8 bits wide, called sum, and another single bit registered called CO. It's our carry out. And here we're going to use a write statement. We want to print out a hex value, which will be this value here that it evaluates. And so in this case, there's no assignment or anything, so it's just evaluated using 8 bits. So when you add these two together, results 8 bits, and you're going to get 0 because it's going to be truncated. The result would be a 9-bit number otherwise. However, in this case, now here this is the concatenation operator, remember. We've concatenated 2 values together, so the size of this is 8, size of this is 1, so the size of this concatenation is 9. So the size on this side is 9, remember. The size on this side, though, would be 8, but we use the maximum of both sides. If we go back to our table here, right here, max of size I or size J. Okay, so it's going to get evaluated using 9 bits on this side. Okay, so in this case, the sum will be 0, and we'll get our carry out of 1. Michael, for some reason I can't open my chat window, so I don't know if anybody asks me a question, relay it to me or let them on or something.
Yeah, I'll forward any kind of questions. Nobody's asked anything.
Okay.
And, your microphone should work, so you can ask with that, or just send a question to me, and I'll make sure that you.
Okay. All right. Here I've defined a bus, 64 bits wide, and I said bus equals tick BZ. So I want you to start thinking about what is going to be the final value of bus based upon what we've talked about in the past here now. Okay, so let's take a look at the answer. Let's go through. Remember that we did not put a size here on this, so the default size is 32 bits. So tick BZ, that's going to evaluate the same as 32 tick hex ZZZZ, so on, where each Z is 4 bits. Okay, so the size of tick BZ is 32. The size of bus, however, is 64. So in this case, we got 64 on this side, we got 32 on this side. So we do this based on the maximum of either one of these, which in this case is 64. So the size of this expression is 64 bits. So that means we resize this tick BZ to 64 bits. And how's it going to do it? With 0 filling. Okay, so that's what this is here. So the final value is going to be 64 tick hex this value. So the important thing here is to refer to that table. Just remember that when you do operations that they have size associated with them, and to go and refer to that table. Okay, now we're going to talk about something a little simpler, just a write statement. $ write. There's a lot of $ statements that you'll see as you get used to running Verilog, things that you can do, like in this case it displays the formatted values. And we can have different specifiers like binary, octal, decimal, hexadecimal, and real. And let's take a look here. In this case, we have a write statement, and we've started off in quotes. We have some stuff that we want to write out, and we have a %0d. We're going to want to print out a decimal value, so this error count is going to be printed out for this. And then for this next part of the statement, the binary value of data will be printed out, and the binary value of expect will be printed out. You can also do it in this format. Looks a little better. So error count goes to that one, data goes to that one, and expect goes to that one. Now again, we're not going to do the labs. In my class instruction I usually stop and do the labs at this point, but I'll post the labs in little videos like I did for the last ones. But in the lab you're going to learn to use various operators. You're going to witness the effect of the operation sizes. You're going to use registers as targets of assignments. You're going to use concatenated assignment targets, and you're going to learn the difference between a vector and a memory. So this exercise for this lab will be to go over what we just did. Now we're going to look at flow control statements. And the first one will be the if statement. If you've had any programming, you're probably going to know most all of this. Flow control is based on a Boolean expression. There's an optional else clause, and the else clause is associated with the closest if without an else. So here's the basic syntax. Again, this statement could be a single statement or a compound statement using a begin and end. We'll look at some examples. The else, of course, is optional. That's what these brackets mean for now. So this is just the basic syntax. So here's some examples. If reset is equal to 1 tick B1, then Q gets defined as 1 tick B0. So that's a simple if with a simple statement. Here we have a simple if and a simple else statement. Now in this case, you have to remember what we said in the last slide. This else belongs with this if. Okay? Oh, sorry. And here's another example. Here we used a begin and end, which specifies this from begin to end. That's considered one statement, but it's a compound statement, so it matches the syntax that we talked about right here. It's still a statement, just a compound statement. And you can put as many statements, single statements, between begin and end as you need to. So it's a good idea to use the begin and end, so it makes it easy for you to see the layout of your code, what you're really trying to do. Now in this case, this else belongs to this if. So if select is not equal to 1, it's not going to use this else right here and set data to tri-state. Okay? Because this else belongs to this if, and this is the same as one statement for this if. So what you really want to do in this case, if select is equal to 0, you want it to set data equal to tick BZ. This is the way you need to describe it. Okay, so if select is 1 and we don't have a read, we don't do anything. One guideline here I have is don't rely on anything non-zero to be true. It's better to perform an explicit comparison, so that's what this is about here, just explicitly compare it. Because remember, Verilog is a 4-valued logic system. So when you're simulating especially, you can have z's and x's. Now in real life, if you're doing RTL, you're going to have zeros and ones all the time. But remember, it's a 4-valued logic system. Verilog's not just for generating RTL and for generating code. It's used for simulation purposes too. So let's talk about the case statement now. Control flow is based on multiple choices. And it's a better style than just using a long sequence of if-else statements. You can also have what's called a default choice to use it like a catch-all. And if no match is found, the case statement is ignored. X matches X and Z matches Z. Here's the syntax. Case, and then you'll have an expression between parentheses. You'll have what's called a choice list, and this again can be a comma-separated list of expressions. Okay, and you can have, and then you'll have a colon and then a statement, and then you could have multiple of these. That's what the curly brackets means here for the syntax. The default statement is, of course, an optional statement. That's what the brackets mean here for this. So let's take a look at some real stuff here. So here, let's say that I've declared bit to be just a single bit wide, and in this case, here's a case statement, case, bit, there's our expression. So now if bit is equal to 1 tick BZ, it'll write this out. If bit is equal to 1 tick BX, it'll write this out. If it's something else, not going to do anything. So here's another example. Now in here we have parity, we'll say parity was 2 bits wide. Here are different values, and here we've included a default. I'm sorry, that should be a lowercase. We should use lowercase for our keywords. That's, I need to make a note of that. Or I should throw that in the lab, maybe so you'll get an error. Okay. In this case, here's a comma-separated list. Now again, this could all be on the same line, or in this case, it looks kind of nice just to actually separate them with a new line. So values of 2 and 3 is going to give p equal to none. Okay. So this just kind of shows you the basic format syntax. A case statement is a true if-else replacement. Choice lookup is done at runtime, and the first match found is executed, and the remaining options are ignored. And you can have redundant entries, and choices can be expressions. So let's take a look at some more. Here we have a that case bit again, except this time we've added in X and Z. So remember, and this is very useful to use X's and Z's when you're doing simulation. So when you write RTL, you're not going to have this type of stuff, but you're not going to be doing writes either. So this is very useful for simulation purposes. Now this looks a little unusual. First time I saw it, I thought, wow, that's really strange. Here the expression is not a register or some memory or some value. This is actually a logic 1. So we put 1 in here. So what does that do? So it's equivalent to if 1 tick B1 is identical, this is the identical operator, identical to reset, then Q equals 1 tick B0. Else if 1 is equal to set, Q equals 1 tick B1. Otherwise, Q is equal to D. So that's sort of a unique way that you can actually do things. One of my guidelines in using case statements is always put in a default clause to handle all the possible values that might come up. So if there's nothing to do, use a null statement rather than fall through. So in this case, we listed all the values plus a default. Now why would I have a default here if it's a 2-bit wide value and I've covered all of the 0, 1, 2, and 3? Well, you might have X's or Z's. So that's what you'd throw the default in there. Now we also have what's called a case Z statement. It's like the regular case statement, but any Z or a question mark in the selector or a choice acts like a don't care. So here we have case Z, then some opcode. We have 4-tick B0001 in a statement. Okay? So my question here now is, which statement will be executed if opcode is equal to 4-tick B0101? I wonder if I can get my chat here, because it'd be nice if somebody would type me a chat message. Anybody want to respond? So in this case, in the first one, it's going to be statement 3. Well, let's go through it and take a look. Well, it doesn't match that. Okay, so we've got all the values. It doesn't match that, okay, because there's no 1 here. So now we look at this one, 0101, 01, that matches. And then question mark, okay, that's a don't care. So, okay, a don't care with a 0, that's all right, that matches. Same thing there. That'll match a 1. So this, it's statement 3. So let's look at the next one here. Oops, I clicked your answer too soon. Let's look at 0Z01. All right, the 0 matches. The Z will match, since it's a don't care. And then 01 matches, so immediately it's the first one. So now what about the next statement? Somebody in the audience want to give me the answer for that one?
1.
Correct.
1.
Correct. And why is that? Well, again, the only thing here that is not identical to what's up here in the first statement is this bit, but since there's a question mark there, it'll match that 0. That's okay. So that's why it's 1. Anybody want to give me an answer for the next one?
Five.
Good answer. Okay, so let's move on. We also have what's called a case X statement. So now any Z, question, or X in the selector or choice acts like a don't care. So now, somebody give me the answer for the first one. 4-tick B0101. No takers? All right. Number 3. The 01 match. There's no match here.
3.
First, yeah, 3. Okay. Anybody want to give me the next answer? Okay, the next one.
1.
The next one is 1, right. Okay. So the Z in this case is like a don't care, so that'll match. Anybody for the next one?
1.
Correct. Okay, and for the last one. All right.
It's like 1 again.
It's 1 again. Okay, so you may want to look at this, the recording later on, if you had any trouble with this, and take a look. See if you understand it. So in Lab 2.2, you're going to learn how to use the if and case statements. You're going to learn how unknowns are handled in the if and case statements. And you'll see how a case statement can be used to model a finite state machine. And I'll try and have these labs posted within the next day here. I have to make the videos for them actually, which will be the instructions. So now we're going to look at loops. And we're going to first look at the forever statement. And it repeats a statement indefinitely. So here's a syntax and an example. So in this example, it just keeps inverting this value. We'll assume that this is a 1-bit wide value for now. And so it just keeps toggling between a 0 and a 1. Assuming it started off as a 0 or a 1. So repeat. Repeats a statement a fixed number of times, and the repeat count is determined at the start of the loop, and it cannot be changed during the iterations. Okay, so here's the syntax. Repeat some expression, number of iterations, and then a statement. Of course, it could be a compound statement with a begin and end. So here we go. We said repeat 1,000 times, write, I will not Xerox my butt. Now this is known as the Bart-Simpson model. Here we have a case of repeat. 16 times it's going to do this statement, and this statement is between the begin and the end. So this is a compound statement. So in this case, it's going to do a reversal on word B and put it in word A. Okay. The while statement repeats a statement while an expression is true. The expression is evaluated at the top of every iteration. So you have to be careful because you can create infinite loops here with this. So here's the syntax. And here's another example which should be similar to our last one. So I said while I is less than 16, do this. Okay. So now I'm going to ask you the question, what happens if I is declared as follows? I've defined I as a 4-bit register. Anybody have an answer?
It's just going to keep going.
Okay, can you tell us why?
As the register is going to overflow. It's three bits will represent 16.
Right. Yeah, we can never get up to the value of 16 to quit the while loop because I can only hold a value from 0 to 15. Okay, so we also have what's called a for statement. It's a shorthand form for some while loops, and so it's a better style for counters. And here's the basic syntax. Okay, and what it's equivalent to, if you want to see what it's equivalent to using a while statement. So we have for some register assignment, then some expression where you're evaluating something, and then another register assignment, and then a statement. So let's take a look. Here's an example of that same bit reversal for word A using word B. So we say for I equals 0, that's our initial value. So it's going to do it while I is less than 16, and then it's going to increment at after it does each at the bottom of this loop, basically. And one guideline is to use a repeat statement if not using the iterator in the body of the loop. Now in this case right here, the iterator I is used in the body of the loop, so this would not be a good place for, you couldn't use a repeat statement here. But now in this next example, we said for I equals 0, I less than 4, I equal I plus 1, we're just going to toggle this clock signal back and forth. So you may as well use a repeat because the I value is not used anywhere in the statements. So that's a better style. So in the next lab, you're going to learn how and when to use the various loop statements. You're going to learn the difference between the always and the forever statements. And you're going to learn to recognize common mistakes that create infinite loops. Now we're going to talk about subprograms, and these will be functions and tasks. Functions, they're used for encapsulating repeated computations, and there's no delay statements to go in them. You'll learn about delay statements later, but just remember you can't put any type of delay statements in. They must return a value, and you can return a register, an integer, a time, or a real. And they're returned by assigning to the function name, and we'll show you examples of this in a minute. The arguments can be input only, single and multi-bit registers only, and you must have at least one argument. So those are the rules. So let's take a look at the syntax real quick. With a function, now the brackets mean this is optional. You can have a type or a bit range, and then the function name, and then one or more of these input with a bit range, which is optional, with an argument name. So this is just all the syntax. It looks a little bad to have to look at it. So let's look at how it's declared in a module. Okay, you can put your function anywhere within this module, and you have function and end function, okay, and whatever else goes inside of it. So here we have an example of function parity. Now if we go back, see we have function parity. We're not doing this part, this optional part right now for this example. Then we have input with a bit range for the size of this word. So that matches, that's what this is about right here. And you can also have optional local register declarations, but now we didn't do it in here. We just had a couple of these inputs. So we had two inputs. Then our statement here is a compound statement. So here's what we're doing for our calculations or whatever, and then end function. Now here's a function, and in this case we said that it's an integer. So let's go back just so you can see that the type. So the type of the function is integer in this particular example. And we said that it has an input 32 bits wide called word. Now the function name itself is an implicit register, and it can be used to compute these intermediate results. So you see here in the calculations we're actually using the name of the function as a implicit register here. Okay, so we're doing calculations with that name of the function. So now let's look at another example. And notice in this one we've declared an integer called I so that we can use it within the function. So if we go back to that syntax, that's what this part of the syntax is, your local register declaration. So you could have one or more of those. Okay, and then in here there was a for loop and some calculations here. So notice here that the function name is reverse. It too is used in the actual calculation because we're going to reverse this byte. So the result is in the name of the function, reverse. So functions are called in expressions. They become new operators, and here's an example. So here I've called the parity function with the two values. Is somebody trying to say something? Function, you use the function within the module. Yes, I think we showed that. Before it is declared, before it has to go in the module. Is it legal to recall a function declared in module A from module B? No. Don't believe so. I have to double check, but I don't believe it is. So, oops, sorry. So here we have a couple of examples. If we called the function, and remember it returns the value right here. When you call it, there's going to be a return, and so we're comparing it in this case to data in. We're using the identical operator and determining whether we have a parity error or not. So that's just calling the function. It returns the value right there, and we're doing a comparison. Here we're assigning it to data, the value returned by the function reverse. So these are a couple ways that you can use it. I lost my chat window again here. Let me see if I can get my chat window back. I'm sorry if I'm missing your questions. I am having a little trouble with the chat window. Okay, let's continue on. Tasks. This is the last item we'll talk about for today. And tasks are used for encapsulating repeated statements. They cannot return a value. Tasks are only used in behavioral code, And behavioral code is code that's not synthesizable, okay, used for simulation purposes. It's not what we call RTL code that which is the subset of Verilog that you use to create real hardware. So you'll use these a lot in simulation. So the arguments are input, output, or in-out, bidirectional. They can be single and multi-bit registers only, no integer, time, or real. So here's the syntax. So again, we have a similar type syntax thing, a little different though. And they're declared within a module. Here we've declared a local register called temp that's 8 bits wide. And here we have two registers, A and B, that are in-outs, either direction. Okay? So I can assign temp the value of A, then I can assign A the value of B, then I can assign B the value of temp. So we've swapped these two, A and B, so to speak. So tasks are invoked as a statement and become new statements. Here we have an example. First, let's say we just write out Word, whatever we had in Word. And here's these two arguments we had, A and B. We're going to send it the upper part, the upper byte, and the lower byte, and then you write it out again and you'll see that it's reversed. So you could try this as a simulation. So in lab 2.4, what I want you to do, I'm sorry, back again. You'll learn to recognize common syntax errors in functions and tasks, and you'll learn how to use functions and tasks. And you'll learn how arguments are passed to functions and tasks. So you need to get a little feel for that. That's all I have for today. Let's take a look at my chat here again. Somebody asked, did one of your function examples use the function name as a value? Yes, it did. They are used for values. And I think I explained that. Let's see. Back to functions here. Yes. Okay, the function name, just remember the function name's an implicit register itself. So in this case, it's an integer register. Okay, so in my calculations down here, I can use lsset, the name, as an integer. Okay, so I can do my calculations or comparisons or whatever I need to do down here in the body of the function. Okay, does anybody else have any questions? One question I have for everyone that's listening is, I know there's been some questions about the video format that we're saving this in. We're going to try a couple of different video formats for saving tonight, and I'm going to try doing an MP4. I know some people are on Mac, some are on Linux, some are on PC, so we're going to try and find a little common ground here if we can, so I don't have to make so many video files.